Let's welcome Jason.
Good morning. Thank you for the introduction, Lidong, and it's my pleasure to be here. And also, first I want to say congratulations to MSRA for 20 years amazing achievements. I have the pleasure to serve on the technical advisory board of MSRA in the last 6 years, and truly, enjoy working with a lot of colleagues here. And it's just amazing to witness the fantastic growth of the research institute. So today, my title is on automating customized computing. So let me say a few words about the customizable computing first. So you are all invited to be here for this event. Let's say we'll offer you the soybean milk and the fried doughs for breakfast, beef noodles for lunch, and Peking duck for dinner. That sounds pretty good, right? But it says, well, if you accept this invitation, you're going to eat it for the next 20 years. There's no way that I have my own unique taste, and I'm not going to live with this, right? But amazingly, that for your CPU processors, you have been very, very tolerant. That in the last 20 years, so if you have some computation to be done in a power-efficient way, you use ARM. For your desktop or servers, you use either PowerPC from IBM and the x86 from Intel, AMD. For most of your computations in the last 20 years, why you can tolerate that inflexibility, right? So that's kind of the issue I want to address. So back 10 years ago, in 2008, we submitted a proposal to the National Science Foundation. We argued that the future should be customizable computing. This is after everyone was going after parallelizable computing, right? We says, yeah, parallelization is very important, but the next step should be customization, where you can adapt the architecture to the workload. So we were fortunate, we got funded by one of the largest program of NSF in information technology called Expeditions in Computing. That's $10 million over 5 years. So we did a lot of work in this direction. So not only customized computing give you freedoms, there's really very tangible benefits doing customized computing. In fact, our research was inspired by an early study of my colleagues, Professor Ingrid van der Heide at UCLA. For example, she gave a very compelling case study on encryption algorithm back 15 years ago, 2003. She says, well, if you look at the case doing encryption, if you design a customized circuit to do that, let's make sure that's being the baseline. The third line is actually the case you do write assembly code on ARM processor. That's already 85x away, that the intermediate efficiency. The next line is writing assembly code on a Pentium processor. At that time, that was the best desktop kind of a processing technology, right? That's 800x away. The last line we did put in the proposal. So basically, you have a Java on the embedded processor. That's several million x away, right? Basically says there's a huge gap between the customized solution versus general purpose solution. So you may say, well, this is a pretty old study, but we look at some other papers, and this is, I'm quoting a study out of Stanford, Mark Horowitz's group, looking at H.264, right? A much kind of a more modern workload. Still, that they showed even after you consider SIMD, that customized instruction fusion, and there are still about 50x gap between the ASIC and the general purpose processors. Obviously, you cannot have a dedicated circuit for everything. So in fact, I'll come back to show you on the left table the second line where you have the word FPGAs. So that's actually a very promising solution. So first, some of the students here might be curious. They say, wait a second, I learned that all this wonderful mononomial architecture in my computer architecture class. Why it's so inefficient? You are saying it can be 80x, 300x away from the customized solution. Why is that? It's actually very easy to illustrate. So think about it. How would you do an add instruction? The first thing is that you got to get the instruction that from the cache or memory into your the processor pipeline, right? So in fact, in this case, it's actually a few percent of energy being consumed already. So that's actually 9% of energy. So the next step, you got to decode, whether it's add or multiply or some other instructions, another 6%. And then remember, the modern processor allow you to do out-of-order processor, so they may actually rename your instruction to avoid some of the conflicts. So that's 12%. And you get the data from register files, another 3%. And then now all the data are available, so you have to wait and to be scheduled to execute in a reservation table. That's 11%. So finally, you do either floating point or integer point execution. So that's where that 14% comes from. And there are some pipeline registers, other things make up the rest of 23%. Among all these steps, right, all the energy being consumed, which one is useful? It's actually the add operation. But however, in order to execute that, actually I have this entire pipeline working for me. So that's where the inefficiency coming from. So now our proposal was quite simple. We says, well, we see the limitation. So let's make sure majority of the computation is actually done on a customized accelerators, not on the general purpose computers, right? So this actually presents a rather fundamental departure from the classical monomial architecture. You may ask the question, why now? That we have learned about this for the last 60 years. So there's a very good reason. The monomial architecture is a very, very elegant solution when you have a limited amount of computing resources. I see a lot of students here, if I ask a quiz, right, how many vacuum tubes were there that in the first electronic computer, right? Or I can ask the question, how many transistors are there in the first microprocessors, right? The answer is not too many. In terms of the ENIAC, ENIAC, right, the first electronic computer, arguably first the electronic computer, you have about about 60,000 vacuum tubes. And the first microprocessor is even much less, 2,200 transistors. So with that limited resources, how can you do all the instructions? The only way is to go through a common pipeline multiplexing. So that's where all the overhead is being spent, but that was the constraint I have. And now we have a different constraint. You should feel very proud. In your pocket, you actually carry somewhere around 1 to 10 billion transistors just in your smartphones. The constraint is that actually we can put in more, but actually the constraint is that they cannot all operate at the same time. Otherwise, the battery will be gone in no time. So we are now switched to an energy constraint situation. So that's actually why that we need to think about alternative architectures. Let me tell you a story. For example, this is a wonderful hotel. I got in over the weekend. I was walking around, and yesterday morning I saw two men working very hard. One person dig a hole about 1 meter wide, 1 meter deep, and as he move on, the second one comes in to fill it up. And then the first one goes another 10 meter, dig another hole, 1 meter wide, 1 meter deep, and after a minute, the second one comes in to fill it up. And then repeat this 3 times, 5 times, 10 times. I cannot resist. I walk up to them and say, hey, gentlemen, what are you doing? That you're working very hard, but you're not accomplishing anything. They stopped looking at me. He says, well, you must be a professor coming from US. Why you ask these silly questions? And he says, we are working as told by our supervisor. In fact, there's supposed to be a third guy who is planting the tree, but he's sick today. So what's the message? When you have 3 guys, you should never customize, right? You should be able to do anything that by everybody, right? But at the scale of Microsoft, for example, when you have over 10,000 employees, you absolutely have to customize. In fact, if you look at our society, we customize in a big ways. So that's why you get lawyers, you get doctors, you have engineers. If you get sick, you don't go to see a lawyer, you see a doctor. In fact, you have to specialize to see whether it's a surgeon or internal medicine specialist, right? And now our brain has about 100 billion transistors. It's also specialized. I ask many neuroscientists, I don't see a pipeline that executing instructions step by steps. We have a whole bunch of neural circuits. Some of them are for motor control, some of them are for language processing, some of them are actually for speech recognition, right? So I call them accelerators. So that's actually the architecture we want to get to that eventually. So now let's talk about a customization. A lot of you heard about this tensor processing engine from Google because it just came probably one of the first for AI 2 or 3 years ago. They also have another generation came out. So they came about over 100x more efficient than CPUs. But that's Google. How many of you can afford to build spend tens of $1 million, wait for 18 months to get a processor? It's not a general, it's not a general solution to all the problems. The second class of solutions, actually, I feel quite excited, was mentioned quite a bit in our proposal 10 years ago to the National Science Foundation. It's called FPGAs, stands for Field Programmable Gate Arrays. A lot of you probably use it in your digital design labs, right? So this is a wonderful integrated circuit. You can have it in your office, on your desk, and you can program it into different the applications. The key of that is that the logic blocks can implement any key input functions. That sounds very fancy. Yeah, well, how can I design something to implement any key input functions? The fact is very easy. K input functions, Boolean functions, has a 2 to the k, the size truth table, right? Just put the 2 to the size k, SRAM there to store the truth table value. That's it. You can implement any k functions as you need, k input function. And then, of course, you got to put in the programmable interconnect to make sure that they can be connected in a proper way. So that's type of devices we're talking about. So today you can buy these FPGAs, put it in your servers. In fact, at UCLA, we use all of those and a standard PCIe on a server. And then the next one was that you have actually a few FPGAs integrated on the memory bus directly. And here is the Caffe. You can do memory coherent computation on PCIe. Intel, actually, they recently bought Altera, the second largest FPGA company. They give us 2 devices. One is that both of them have the PCIe, have the FPGA connected to CPU on the QPI bus directly. QPI was used for a system that the CPU to CPU connection took away one of the CPUs, put in the FPGAs. So all these platforms available, you can actually do it. At UCLA, in fact, about 5-6 years ago, we started building clusters using these devices. On the left-hand side, we have something built on a Zinc FPGA. This is an ARM processor with a lot of programmable fabric. Each one is only 2 to 3 watts. Then we have a collection of them, become a mini supercomputer, very, very low power. On the right-hand side is more like a server class, that the architecture, that you have the servers that with a FPGA, that PCIe card. So in fact, it's very proper to talk about this topic here at this conference because Microsoft is a clear industry leader on FPGA-based acceleration. About 4 years ago, and they announced that they actually use FPGA to accelerate the bin search engine. In fact, the work started even earlier. So that was actually a very impressive result. They deployed a very large scale, over 1,400 servers. And more recently, about a couple of years ago, they had an announcement, a very unique architecture. They can have all these FPGAs connected to the top of the rack switch, and it goes to L2, L3 switch. Basically, you have a sea of FPGAs connected and to be a configurable fabric for any applications. And they chose to, guess what, the AI applications to accelerate the machine learning. So these actually, what I'm saying is that these platforms, hardware platforms are coming. In fact, if you go to Amazon, you can just put in your credit card. They have a cluster called an F1 cluster. You can use FPGAs together with CPUs. I'm teaching my CS259 class this quarter. I have to give them a midterm exam so that I can come here to speak. Then, so their lab project was all doing CPU plus FPGA co-designs and acceleration on these platforms. We stopped building some of these hardware platforms because it appears in the cloud. We just use them. But the question, however, is how do you program such a beast, right? That the multi-core programming is already very, very difficult. Now you add this heterogeneous hardwares, and how do you do that? I want to convince you that there's a way to program it. In fact, my whole career in the last 25 years is working on this topic. First, some of you may know this paper we wrote in 1992. Basically says, well, if you have a Boolean network, I can actually map it to a lookup table-based network on FPGAs in minimum depths and also optimally in polynomial time. So that was considered to be a rather surprising result because a lot of the problem was NP hard, right? This is one case. You can take a general application, I can map it to a minimum level of a lookup tables and through a sequence of a network flow computation optimally. So this is used in all the FPGA compilation tool today. So you may say, well, how do I get a Boolean network? I don't normally design Boolean networks. That's true, but so that's actually, the research continues. About 15 years ago, we started a project called the high-level synthesis. You don't design Boolean network, but you write C programs, right? So we want to compile C programs into Boolean circuits in an automated fashion. In fact, we have done that successfully with, at that time, the LLVM compilation infrastructure just came out. We make use of that. Instead of going the backend goes to the various kind of CPU processors, we have the backend generating the customized circuits automatically. In fact, this project went quite well. We spin off a company called AutoESL 2006, and that company was acquired by Xilinx 2011. So some of you might be using the Xilinx Vivado HLS tool. That's all coming from UCLA through this startup. I want to assure you that, in fact, this can produce very competitive results. At the time, Xilinx made the acquisition. They did a very detailed comparison. They look at, for example, one of the wireless application. They had a manual design, the RTL code base. They compare with the automated high-level synthesis solution. So this is a very good case where 11% to 30% better in performance, in areas, right, with comparable performance. You have to set the frequency to be the same, 250 megahertz, 225 megahertz for both implementations. So that's actually exciting. Now you can write C programs to do circuit design, a lot closer to what we are doing with general purpose computation, right? So that's the good news. And in fact, after this tool came out, the Xilinx did a great job that, for example, my class, I'm teaching today, actually give them this option. You can use the Vivado HLS. You just do a Google for Vivado HLS. There's 2,500 of hits just in research papers. There's tens of thousands usage in the industry, right? So that's the good news. But the bad news is that the high-level synthesis alone is not sufficient. The reason, there are two reasons. The first problem is the growing semantic gap. So we finally can let you to program FPGAs using C, C++, not using VHDL or Verilog. But look at the upper curve. The software world is going wild. First they go from C to C++ 11, 14, 17. But moreover, there's all these domain-specific languages. For those of you who are doing AIs, and you know the TensorFlows, the Caffes, the PyTorch, and MXNet, right? So all of those. So that's actually the problem we're facing. The second problem is that for some of you, if you ever actually did a high-level synthesis design, not every C program give you good solutions. Let me give you one example. This is typically my first year graduate students who will go through this problem. They take this Needleman-Woods algorithm, for example, for sequencing alignment. They got a C reference code. They compiled it. They did get an architecture. They get a circuits right away in a matter of minutes. So very excited. So great, the high-level synthesis works. The only problem is that it's 100x slower than the CPU, right? If you sit down, you look at it, why that's the case. First, they actually pass all these characters over as parameters. Each character is 8-bit wide, which means when you do the memory read, you only read 8-bit data. My memory bus is 512-bit, right? So it's actually a fraction of a bandwidth you are using. Not only that, they don't have cache automatically when you generate the circuits. So you're reading main memory every time. So that's much, much slower than the logic itself. We took cache for granted in all the CPUs. So this is actually a surprise. And you got all these loops that if you don't do anything, they will be kind of scheduled in a sequential fashion. And then finally, you may actually get some parallelizations and through pipelining other things. They all read the common memory block. That's actually a killer because the memory on-chip memory block has only 2 ports, which means that actually only 2 data can be read and write. So that's impossible to get the high performance. So these are the things you have to learn how to overcome. Of course, when they get to the 2nd year or the 3rd year, so they learn how to write a better high-level synthesis program with all these programmers to enable coarse-grained parallelization, data tiling, coarse-grained pipelining, fine-grained pipelining. Now they are getting 10x speed up to do that. So that's great. So they get their first application out, and they start building another application after 3 or 4 applications, they can graduate, right? But this is not very scalable. And we want to make sure everyone in this room that with a decent IT training, you got to be able to enjoy the experience of a customizable computing. So that's actually what we want to do. So I use this term that we want to democratize customizable computing, basically make it accessible to the average the IT professionals. So this is in our current research scope. We really want to bridge this semantic gap. You can see we started from high-level the domain-specific languages. This could be Spark, used for big data processing, Halide for image processing, and others, machine learning, and the Caffe TensorFlow there. And we have an intermediate representation called the hetero-CL, which I will talk a little bit more. But then we're going to do this automated microarchitecture optimization. Remember all the illustration I gave it to you, you get poor performance because you have no idea how the good microarchitecture looks like. So we're going to do it for you in an intelligent way. And can be systolic array, can be stencil, can be composable, parallel pipeline architecture. And so other the patterns that are being added. So as I said, our goal is to democratize the FPGA accelerator design. So all of you that can actually do it in a very minimum effort. In fact, the students in my class actually going through this exact same exercise. We have some wonderful tool called the Merlin compiler. They're using that. So let me give you some examples of what we do as part of the optimization process. One architecture we explore is called a systolic array. It's a very old concept that basically, the communication is expensive. In a systolic array, I only talk to my neighbors, my left neighbor or my right neighbor, right? In 2D systolic array, you can actually have 4 neighbors, right? The good thing is that I have only local communication. My circuit can operate at very high speed. Now the first question is that what application can be mapped to a systolic array? And then the second question is, can you explore all the solution space that are available, right, for a given application using systolic array architecture? So this is not easy. I'm quoting the data from Intel. They did a systolic array for example, machine learning acceleration. And they're talking about up to 18 months manual designs. So this is clearly not acceptable. So we actually developed a compiler called PolySA. Stands for polyhedral, based optimization. I will not go into too much of the details, but the idea is that your time-consuming step typically is a nested loop. May not be a perfect nested loop, but it has loops. And the loops can be represented by a polyhedron in a high-dimensional space. Depends on the iteration domains you have. From there, we can actually come up with a way to map it to a systolic array automatically. And for example, that's matrix multiplication. From a polyhedral compiler will get you a polyhedral representation. And so this is in a matrix representation form. And here you can capture the dependency and then from there to do the mapping. When you do the mapping, you care about 2 things. One is that you care about the so-called processor assignment. Do I use 1D or 2D arrays? So this is actually an example. We talk about the projection going upward, and so I will get a 2D array when I project that, right? The second vector is actually how I'm going to schedule the computation. I'm showing you actually an interesting scheduling algorithm. The vector is that it's going to go through this diagonal way to schedule. For example, t equal to 0, t equal to 1, t equal to 3. So in 4 steps, I can do all the computation. And the key is that you can see when I schedule that, I make sure that I do not break any dependency, so that's called the causality. And also, I don't have 2 computations on the same processor at the same time. That's called availability. So I have some mathematical constraints about that. So eventually what I need to do is to be able to search in this design space to find out all the possible solutions. So let me show you some, in fact, before you do that, there's actually a problem. Is that, for example, some of you knows about the convolutional neural network. That has a 6-level nested loop. So you may have to do multiple level projections. So that's one. Number 2 is that if you have a systolic array, your data can only coming from the boundaries. You don't want it coming from the middle of an array. So that you have to make sure there's some optimization to take care of that. Some of the array elements works pretty slowly. That takes 10 cycles to do one operation. You don't want them to wait for another 10 cycles. You can pump in other applications. And finally, you can get a very large array. You got to partition it into smaller array to fit on your FPGAs. So, but anyhow, so we have an automated flow. You can see for matrix multiplication, we can show you these are the 5 possible systolic array you can have. And the 4 of them has been discovered in various kind of publications. And the MM4 is something new that we showed that's also viable. For CNNs, convolutional neural networks, where we quoted early on for the ImageNet, right? So this is a lot more interesting. We show there are actually 15 viable configurations. And this configuration number 5 has been published out of MIT, the Aris's work. And this number 8 has also been published out of UCLA, Peking University, and the Falcon Computing. So that was actually a year ago. But now we show these are not only 2 systolic arrays you can have. You can actually have all the 15 systolic arrays. So that gives us a much larger solution space to look at it. Right. So another kind of architecture example I want to give it to you is the stencil computation. Because image processing is very, very important. If you do image processing, you probably notice one important application is the so-called stencil computation, where you want to update the value of this pixel based on the 4 nearby pixels. So in this case, I would do a deep blur, blurring operation, but you can also reverse that to do some image sharpening. In order to do that, it's actually quite challenging, because if you want to do this computation in 1 clock cycle, means that these 5 elements has to come out with 5 different memory banks. Not only for this one point, but for all the points as I go through my images. Can you do that, right? But not only that, it turned out that the life is more complicated, because I may actually want to do want to process multiple pixels simultaneously. So that's why you can actually have this array that with multiple points, you want to make sure they are all in different memory banks. So this is a very challenging design. This application is absolutely memory bounded, both on-chip and off-chip. So if you're not careful, even the on-chip memory will saturate your bandwidth. So with one actually stencil processing, we can actually do that with some clever arrangement. But the most recent breakthrough we have is that now you can give me any parallel computation, multi-stencil processing. We can actually come up with an architecture to do that. So that's actually the processing we have. So this is actually animation to show you how we're going to do that. Every time you move forward, we actually have you a customized memory architecture where we have a few FIFO chains together with the proper breakpoints, and we can read out values out of these breakpoints. That I can guarantee I can get all this memory access from different memory banks. simultaneously in one clock cycle, and I can sustain the computation across the entire image without any overlap. So that's actually what we have. So you can see that actually the performance we have is actually very good compared to all the previous published configurations. So we are several X faster all the way to the performance up to 3.5X faster. Also want to point out is that for this actually type of architecture, we can have a very accurate performance modeling capability. This is actually is important for us to do very intelligent search to get the best possible configuration. Let me give you one more example, then we can actually move to the end. So a more general architecture we work with is called composable parallel pipeline architecture. Think about FPGAs. You have these millions of logic gates there. You can do two things very, very well. Is that they give you a massive parallelization. In fact, it has the DSPs, it's basically it's multipliers followed by add. They have a 3,000 to 5,000. So there's lots of parallel computation you can do. Another thing it does very well is that it can allow you to build arbitrary pipelines as deep as you want. For example, even 15 years ago when we started a company, Auto ESL, to do high-level synthesis, guess what? The first customer was not any of the semiconductor company. The first customer was a financial bank come to us saying, oh, Jason, can we use your tool? I said, no kidding. What do you use the tool for? They says, okay, we do high-frequency trading. We want to use the circuit to actually calculate that whether we should make a trade or not instead of using CPUs. Because you can beat any other firms by just 1 second. We make tons of money. So they actually do that. So actually the application they have, they didn't tell you as all the application, but the first benchmark they gave it was a Black-Scholes algorithm. It's a very famous algorithm for stock option pricing. So we implement that with 390 levels of pipeline, totally dedicated, customized. So they actually was very happy with the result. But how do we take the full advantage of the FPGA to do that? It turns out that we can actually have an architecture template for you to do this very well. And I call that a CPP architecture. First, you got to do the load, compute, store. So you can overlap computation with communication. So that's an important decision we have. And the second step you can see is that all these memories, and when I do the memory read, I will do the memory correlating so that I can actually do all of them with the maximum memory bandwidth. And when they get into the architecture, when they get into on-chip, actually it's already partitioned into different memory banks so that I can get maximum on-chip memory bandwidth out of that. By the way, this partitioning is a very tricky step. When it comes in, how do you know you can partition it so that there's no conflicts, right? So we actually have a lot of theory goes behind that. In fact, the polyhedral model is also used here, helps to do the analysis that how many wave partitioning is sufficient to do that. And so this is on-chip buffer for data caching and also parallelization. And then here is also very important. You can interleave parallelization and the pipelining in whatever fashion you want, that you can nest them in a very deep way so that you can get a very, very high bandwidth, very high degree of parallelization to achieve that. So this is actually what we have. But however, if you come back, you can say, how do I specify such an architecture? We have a way for you to specify that automatically. Here is that we're making use of this compiler called the Merlin compiler. It's another spin-off out of UCLA about 3-4 years ago. For example, Intel Capital is one of the investors in this technology. So we really want people to use that for compilation into CPU plus FPGA platforms. So in this Merlin compiler, what is important is that it gives you a few parameters to do specification. You can say this is very much like an OpenMP. For some of you who has done parallel computation, you can actually use it to specify I have some coarse-grained parallelization, fine-grained parallelization. I can pipeline these loops, and that's it. So that's basically you have about 3 parameters you can give it to annotate your program about. Here's some parallelization capability. Here's a pipeline opportunity, and then we can generate the circuit for you. But even that is actually tricky because you have to think clearly to know where you can do parallelization, where you can do pipelining operation, how do you combine them together. So this is actually a case where applying the AI technology. Remember that I was telling my students about 2 years ago when you see the news that the machine can be the best chess player, right, to play Go chess. I says, wow, maybe we can just beat the best circuit designer so that with AI technology, put them out of a business, right? So we actually work on that for a while. It turned out that this is much harder than playing Go. Even you can argue Go may have an even larger solution space, but it's a one fixed game. Whenever you fix the rule of the game, the computer can do very, very well. But circuit design is like a program design that there's no boundary. You can come up with any possible solutions you want. So that's why it's so hard. But nevertheless, we actually have a framework to use AI technology to do that. And so within this, you can see this is the key part is that the intelligent design space exploration that allow us to decide where to insert those parameters in what fashion. So on top of this Merlin compiler, and the Merlin compiler can generate the code ready for high-level synthesis tool. So this whole flow, you can actually use it. In fact, before I come to the stage, I just check the tool. That the machine really helps. That I check my lab 2 design was assigned last 2 weeks, and it was due last Thursday. My TA helped me to grade it. The first part 1 was ask students to do designs using high-level synthesis tool. Basically, you write your C program, you add in this program by hand, right? Part 2 was due last Thursday, is that you use this Merlin compiler. The difference is quite visible, so that the average performance out of 15 graduate students in my class was 18,000 cycles to do digital recognition. This is one of the kind of a baby AI problems. Now, with the automated tool, we dropped to 4,000 cycles, right? So there's a huge, huge improvement. That's actually by a factor of 4. The best manual design we ever get was 3,000. So we're pretty close to that. We are not exactly there yet, but we are making a lot of good progress. So this is actually a joint work that at UCLA and also with Falcon Computing. So you can see that they also have a set of benchmarks to show that the manual speed up and automated speed up by the compiler. So it's very close to the manual speed up. And this is actually a set of industry designs from one sector on financial modeling. Again, there are people interested in not necessarily high-frequency trading, but they do a lot of other things that then requires fast computation. So the compiler can give you results 35x speed up, 15x speed up, 4x speed up, very close to manual designs. So that's what we have. So with this kind of a capability, now it's really possible for you to accelerate some of this high-level domain-specific languages. For example, we published a paper about 3-4 months ago at the Design Automation Conference. My student made an attempt to compile Apache Spark into FPGAs. So to do the syntax transformation is not that difficult because you can map it eventually to C and eventually come into FPGA. The problem is that the first try you get a horrible result because with Spark, you have no way to insert any parameters because it's a standard language at a very high level, so you just cannot give any hardware directive to say how you design it. So it was only, in fact, we started a project 2 years ago. We couldn't publish it because the result was too bad. But only until this summer when we started having this very intelligent design space exploration algorithm. So the backend is all automated. So now we can generate this C code. Now the first, at the beginning, we were 500x slowdown. So now with this automated solution, we are 10x faster than the CPUs for a reasonable set of benchmarks. So this is, to me, is an encouraging first step. I have students working on, for example, mapping Halide algorithms into FPGAs. It's a very cool language in the image the processing space. We're also looking at mapping tensor flows into FPGAs. Just one word about this intermediate representation we're working on, because we cannot map every domain-specific language that using a customized pipe to FPGAs. The way we achieve that is to go through this intermediate layer called the HydroCL programming language. So this one is actually an extension of the TVM work out of University of Washington. It has actually both of our work was influenced by Halide. They have this concept to decouple the algorithm specification from the scheduling, or optimization. Basically, you specify your application once, and then you can have another section to talk about all the optimization you want to do. What we have added is that imperable code, we can mix the imperable programming with also the declarative programming. And we allow you to add various kind of high-level scheduling capabilities. For example, you can also indicate the microarchitecture preference, systolic rate versus stencil versus others. And finally, we can allow you to do device placement. So this doesn't have to be only to FPGAs. You can go to GPUs. You can do whatever TPU-like devices. So now our goal is you can write your application once, and then it can be mapped to different implementation platforms. So here's a summary. Let me give you the report card. I think we are making some good progress on the high level, doing this the DSL, domain-specific language, to various kind of heterogeneous hardware. So the intermediate representation is an effort started more than a year ago, funded by Intel. Has a joint project, joint program with the National Science Foundation called the CAPA, stands for Computer Assisted Programming for Heterogeneous Platforms. So I'm working with my former PhD student, Zhiru Zhang at Cornell, and with also Professor Marianne King and Adrian Sampson. So we are actually making a lot of good progress. We expect this will be much more mature in another 6 months or so. By the way, this is an open source project that we have a submission out. We will share the GitHub links that hopefully soon after the paper is accepted. We really hope there's a community adding that different kind of a front end to that. And the back end is now kind of a cup of tea. We have worked on this in this area for over 10 years to map it with different kind of a microarchitecture template, right? The stencil, the systolic array. We kind of introduced this name or invented this architecture, the CPPs, composable parallel pipeline architecture. And I really encourage everyone here to think about what are type of architectures which are suitable for spatial computing, right? That you can actually map it to this customizable hardwares. So now our goal is that to say you innovate, you come up with the better ideas to do the AI, to do speech recognition, to do the intelligent agent that Raj was talking about, and we automate. That you shouldn't even worry about how do you map it to the customers, the hardwares, all this backend. We'll take that for you automatically. So with that, I want to thank all first our sponsors, National Science Foundation. CRISP is a center between DARPA and the Semiconductor Research Association. Actually, they funded 6 centers nationwide. It's a $150 million program, and we are in the center on near storage computing. And we have the CDSC, stands for Center for Domain-Specific Programming, that we have a large list of industry partners, and we hope some of the people, in fact, with partners both in US and China, we hope some of you actually can talk to me to join the program. Of course, that most of the work, in fact, all the work I've done with the army of graduate students, postdocs, and many collaborators. I'm 1 minute ahead of schedule. I'll stop here. Great. Right.